Chapter 7 is on work and energy resources, and it has some really important concepts in it, particularly when we start talking about conservation of energy. So energy can be transformed from one kind to another. You eat a chocolate bar and it goes from being chemical energy of one sort to maybe mechanical energy if you use that chocolate bar's energy to run a mile. So, or if you take a piece of wood, it's got stored chemical energy and you burn it, then that stored chemical energy turns into energy of motion. The molecules move around, heat energy is created, light is created. So the energy is transformed from one type to another. What's great about this is that the total amount remains constant, so it's all there, you just have to look for it. We say that the energy is conserved, and situations where energy is conserved make problems much easier in physics. If we can just isolate our system, if we can keep things from getting lost along the way. So we'll start out with work. In physics, work is defined as force times distance, where the force is applied parallel to the distance the object moves. So force times distance gives you work, but it's force parallel. So the force and the distance are parallel to each other. They're in the same direction. And we'll look at a few examples. In physics, we measure, it's symbolized by a capital W. Work is symbolized by a capital W. And these funny little double lines you see usually mean is parallel to. So force is parallel to distance, or force, distance is parallel to force. So work is measured in joules. Work is measured in joules. The abbreviation for a joule is a capital J, just like the abbreviation for a Newton was a capital N. So again, the force is in newtons and the distance is in meters. Work is a scalar. It is not a vector. It just has magnitude. It does not have direction. So a joule is the same thing as a Newton meter. Newton for the force, meter for the distance. A Newton was a kilogram meter per second squared. So a joule is the same thing as a kilogram meter squared per second squared. Now, we used to use calories all the time. We used to use calories all the time. In physics, calories are the CGS units. We don't anymore. We'll do our calculations with work. The only reason I bring them up is that if you read a food package in the United States, you will see the number of calories contained. So an olive is about 10 food calories. A slice of bread might be roughly 100 food calories. A food calorie and a physics calorie are not the same size. A physics calorie, 1,000 physics calories is the same thing as 4,186 joules. And 1,000 physics calories are the same thing as 1 kilocalorie. The calories on a box of food in the United States are actually kilocalories. And if you buy something in almost every other country in the world and you read the back of the package, if you buy a soda or a loaf of bread or whatever, you won't see the energy content for the food in calories. You'll see it in joules. So, all right, a little bit of culture for us. So work is a scalar. It has magnitude but not direction. So if the force is perpendicular to the distance, then the work done is 0. What does that mean? That means that in order for an object to move horizontally, at least some part of your applied force has to be in the horizontal direction. So let's look at the guy pushing the lawnmower. So we want the lawnmower to move to the right. Pushing on the lawnmower, you push down along the length of the handle. So it's at an angle. We know we resolve into components. So it'll have a component that's horizontal and a component that's vertical. The horizontal part is the part that's in the same direction we want the lawnmower to move in. So it's the horizontal part that would be the F in our equation that work is force times distance. If we are standing still and we're holding our briefcase, but we're not walking, the distance we travel is 0, so we're actually not doing any work. If we are moving horizontally and we can walk at a constant velocity, so we're not accelerating, we're not doing any work at this example either. Now, if we accelerated, we'd do work, but we're not accelerating. If we take the briefcase and we climb the stairs, we are moving. There's two different ways to look at this. You could look at it as we're moving diagonally, so this distance. So whatever part of our force can be in that distance parallel to our direction of motion, that's the force we use in the equation. We'll do an example similar to this. We'll do an example. All right. So we've talked about these. Push against a wall, distance is 0, so the work is 0. Pick up a book. If we don't change its, if we can pick it up without accelerating it, then there's no work done. If you can walk at a constant velocity, there's no work done. There's a lot of different scenarios. So to do work, you have to have a force parallel to the distance you're moving. Let's do an example. So we have a boy pulling a 10-kilogram box with a 20 Newton force at a 30-degree angle for a distance of 30 meters. Frictional force is 10 Newton. It retards the motion. What is the net work done? So we want the total work. We know that F equals ma, W equals mg, and that this little w is lowercase w, and it's weight. Weight is mass times gravity. This W is a capital W, and that is work. Work is force parallel times distance. So we've summarized what we know over here. We need a picture. So we've got our free body diagram. So here is the box. The boy is pulling on the box. The weight comes straight down. The normal force comes straight up because the box is on a surface. Friction, the frictional force, retards the motion. Friction always acts opposite to the direction you're moving in and parallel to the surface. So friction's going to point left. Because the boy is pulling up and to the right, and this little angle, I don't have it drawn in, I know. This little angle here in the bottom corner of our triangle, that's our 30 degrees. So the force of the boy has to be broken up into horizontal and vertical components. Once you do that, we have to write our horizontal and vertical force equations based on the picture. So F total x equals mass times acceleration in the x direction equals every vector pointing right or left. So that would be the force of the boy in the x direction, and that would be kinetic friction. So the force of the boy and friction. Vertical forces, anything pointing up and down. So that would be the normal force, the force of the boy in the y direction, and the weight. Why don't we have just the force of the boy in either one of these equations? Because the minute you make a force the hypotenuse of a triangle, you can't use the force anymore in the equation. You have to use the two legs of the triangle. So we know, because we have an angle theta, we have to resolve into components. And it's the force that's at the angle, so it's the force that we resolve. Should have drawn my little line in between. I'm sorry, I didn't. Let's see. Shape, arrow. I guess not an arrow, we want a line. We're going to change it, make it hopefully a dash line. So sine is opposite over hypotenuse. Sine is, our angle is 30 degrees. The opposite side of, remember the 30-degree angle is the one down here in the lower left-hand corner. So the opposite side would be the y component of the boy's force. And the total force is 20 newtons, so that's in the denominator. Again, I should have drawn my little line. I'm going to do two things on the same page. I need to do that. I apologize. Alrighty. So moving down, sine is opposite over hypotenuse. Sine of 30 degrees is the force of the buoy in the y direction over 20 newtons. So the force of the buoy in the y direction is equal to 20 newtons multiplied by the sine of the 30 degrees. And we need to be in degrees, not radians. I apologize for the little underline. I thought I had caught all of those, but apparently not. So 20 newtons multiplied by the sine of 30 degrees gives you 10 newtons. It points up because that's the way it goes in our drawing. Go and do cosine. Cosine is adjacent over hypotenuse, so the cosine of 30 degrees would be the force of the buoy in the x direction. This is the adjacent side, and then over 20 newtons. So the force of the buoy in the x direction is 20 newtons multiplied by the cosine of 30 degrees, or 17.32 newtons, and it goes right because that's the way the arrow points in our picture. Now what? Well, now we can use, remember when you resolve, you go back and you look at the horizontal and vertical force equations. We are looking for the object moves in the x direction, so we wanted the net work done, which means we probably need the total force in the x direction. This is one of the few times we'll actually need the total force in the x direction. We know that it's the force of kinetic friction plus the force of the buoy. Whoops. Oh, we have kinetic friction. We have the buoy's x component. We can find that. Yay. So force parallel is the total in the x direction. It's the force of the buoy in the x direction plus the force of friction, and we're going to make right the positive direction. So force parallel, the buoy is moving right, that's 17.32 newtons. Friction is pointing left, so that would be minus 10 newtons. So our total in the x direction is our parallel force, and it equals 7.32 newtons right. So the net work will be the force parallel times distance, so 7.32 newtons times our 30 meters, to give you 219.6 joules. 219.6 joules. All right, we need another example. Remember I said we'd come back to climbing the stairs? Well, this is it. Set of stairs, I'm going to have a ramp. Oh, I'm sorry, hill. We have a hill. 10 kilogram box. The hill is 40 meters high. That's how tall it is. So from the bottom to the top is 40 meters. Our path, though, is 50 meters long. And I know, because this is a 3, 4, 5 triangle, that means the base is 30 meters. That's just extra information. You could also go with a squared plus b squared is c squared if you needed it. So we know that mass is 10 kilograms, y is 40 meters, d, the distance along the hill or the path, is 50 meters, and x is 30 meters. We know we're not accelerating. We want the work. Remember, this is capital W for work. Work is force parallel times distance. This is little w for weight. If it would help you to write out the word weight, you could write it out. Weight is equal to mass times gravity. So what are we doing? We have 3 distances and no forces. The force you do when you take something from one elevation to a different elevation, you are doing work against gravity. And so you have to overcome gravity pulling you down. So your weight is the force you have to overcome. So we have to, W will be the force, mg. Now we just need to figure out the distance. So the force is W, which is mg. So 10 kilograms times 9.8 meters per second squared is going to give us the 98 newtons, and it goes straight down. So because it goes straight down, we need a distance in that same direction. 30 meters is in the horizontal direction. We cannot use that. 50 meters is the diagonal. We cannot use that. The direction that is parallel to our force is 40 meters. So we have to use Y. So W is force parallel times distance. So it's going to be the weight times the change in altitude. So 98 newtons times 40 meters, or 3,920 joules. 3,920 joules. Okay, there's some homework problems with that, and then there'll be some study guide questions as well. All right, so we need to talk about kinetic energy and the work energy theorem. Kinetic energy is the energy associated with motion. Kinetic energy is the energy associated with motion. The formula for kinetic energy is mv squared divided by 2. mv squared divided by 2. It is energy, so it's measured in joules. M is mass in kilograms, V is velocity in meters per second. So the work energy theorem tells us that your change in kinetic energy is equal to the work done. So if you are changing your velocity, you are changing your kinetic energy, it takes work. How much? Well, changing kinetic energy will equal the work that it takes to provide that change. Unless there are sneaky places along the line stealing energy, and that means we'd actually need to apply a little more to account for lost energy. We don't have lost energy unless they tell us. So let's look at gravitational potential energy. Potential energy is energy associated with position, and there are different kinds. Gravitational potential energy just means that if you are at a certain altitude above the surface of the earth, you have stored energy because you're above the ground. And if you are just pushed to the edge of your ledge and gravity takes over, your potential energy will turn into kinetic energy. Your stored energy will turn into energy of motion. So the formula for potential energy is PE equals mgy, mass times acceleration due to gravity times your vertical distance above your origin. So mgy will equal your potential energy. You need to know the formula for kinetic energy, and you need to know the formula for potential energy. And again, if you're in a situation where you're changing your potential energy, you're picking up a pencil off the floor and putting it on the desk, you've changed its vertical position, it has a different potential energy now. The work needed to lift that pencil without accelerating it will be equal to the difference in those two potential energies. So just like the work was equal to the change in kinetic energy, if something's moving, if all you're doing is changing its vertical position, the work necessary will equal the change in potential energy. So we have conservative forces and non-conservative forces. A conservative force is independent of the path taken. A non-conservative force is path dependent. Friction is a non-conservative force. Friction depends on the path you take because friction frictional losses are a result of the interaction of two surfaces. So if we pick up an object and move it to position 2, and we pick up the object and move it to position 2, but under a more circuitous route, they actually have the same potential energy change because the change in potential energy is independent of the path taken. Let's look at some conservation of mechanical energy problems. So remember we said energy is conserved. It can be transformed from one kind to another, so from potential to kinetic, but it's not lost. We can account for it. And the equation for our energy is that the total energy is equal to the kinetic plus the potential plus any lost energy in getting there. All our energies are going to be in joules. DE is what we're using as an abbreviation for dissipated or lost energy. So that might be energy lost to sound or heat along the way. So let's look at an example. We've got a 100-kilogram rock. We're going to drop it off a 50-foot high cliff. How fast is it going when it is 20 meters above the ground? How fast is it going when it hits the ground? And we will assume no dissipated energy, no lost energy. So what do we know? We know that our starting velocity, V1, is 0. Our mass is 100 kilograms. We know our starting altitude above the ground, Y1, is 50 meters. And we know our other two altitudes. Y2 is 20 meters and Y3 is 0. And we have 0 dissipated energy. And what we want to find are the other two velocities. Velocity at point 2, which is 20 meters above the ground, and velocity at point 3, which is at ground level. So kinetic energy is mv squared divided by 2, and potential energy is mgy. And kinetic for us, because our dissipated energy is 0, our total energy will be kinetic plus potential at any one location. So what does that mean? That means up at the top, if you take the kinetic at the top and the potential at the top, they add up to give the total at the top. But the total at the top is the same as the total at the 20-meter mark, is the same as the total at the ground. All that's happened as you drop, drop, drop is you're going from all potential at the top to some potential and some kinetic at the 20-meter mark to all kinetic at the ground. So we're just changing from stored energy bit by bit to energy of motion to at the ground, energy of motion. After we hit, we will not be moving and we'll be at 0. But at impact, V3 will not be 0. All right, so let's look at this. Find E total. So at the top of the building, we know E total is kinetic plus potential. So that's mv squared over 2 plus mgy at the top. So at the top, velocity is 0, so kinetic energy is 0. At the top, the mass is 100 kilograms, g is 9.8 meters per second squared, and y is 50 meters. So 50 times 9.8 times 100 gives us 49,000 joules. That is the total energy at the top, but that's also going to be the total energy at Y2 and the total energy at Y3. Now we look at location 2. It's the same equation, kinetic plus potential equals total. Well, we know the total is 49,000 joules. So 49,000 joules is going to equal mv2 squared over 2 plus mgy2. If it helps you, you can put these symbols in parentheses. Looks like I got lazy. So 49,000 joules equals 100 kilograms. V2 is what we don't know, so we're going to solve for that. And 2 is 2. 100 kilograms times 9.8 meters per second squared times 20 meters. So the 49,000 is still on the left side. 2 goes into 100 kilograms and makes it 50 kilograms. That's where the 50 comes from, right here next to the V2 squared. But how about this 100 times 9.8 times 20? Well, 100 times 9.8 times 20 is 19,600 joules. To remove it from the right-hand side, we have to subtract it from both sides. So it disappears on the right, shows up on the left. So 49,000 joules minus 19,600 joules equals 50 kilograms times V2 squared. So 49,000 minus 19,600 gives us 29,400. But we have to divide both sides by 50 kilograms to get the 50 off the right-hand side. 29,400 joules divided by 50 kilograms gives us 588. But that's going to be in meters squared per second squared. And now that's equal to the velocity squared at point 2. To find the velocity at point 2, you take the square root of that 588, and you have 24.25 meters per second. So when you are 20 meters above the ground, this is how fast you're going. Okay, last part. How fast will we be going when we smash into the ground? Same equation, same process, same everything. Same everything. So we're going to look at location 3. E total is kinetic plus potential at point 3. So 49,000 joules equals the mass times V3 squared over 2 plus mgy3. 49,000 joules equals 100 kilograms times V3 squared over 2 plus 100 kilograms times 9.8 meters per second squared times 0 because Y3 is 0. We are at the ground. 49,000 joules goes here. 100 divided by 2 gives me 50 kilograms times V3 squared. This whole term, 100 times 9.8 times 0 is 0. To get the V3 squared by itself, you have to divide both sides by 50 kilograms. So 49,000 joules divided by 50 kilograms would give us V3 squared. And if you take the square root of that, you get 31.3 meters per second. I skipped 2 steps. If you can't do that, include them. And again, I'm sorry about the squiggly. It thinks I've put too many spaces in. All right. Another example. This one is a little, actually it looks complicated, but it's not. It's the box slides down the hill. If you can ignore friction, this is actually a very easy problem because we can use conservation of energy. Yay for that. So the velocity at the top of the hill is 0 meters per second because we're gonna just put it on and let it slide. Mass of the box is 10 kilograms. Y at the top of the hill is 10 meters. D is the distance along the hill. That would be 50 meters. Theta is 11.5 degrees. That would be this angle right down here in the lower right-hand corner. Y at the bottom of the hill is 0, and the dissipated energy is going to be 0. We're going to ignore friction. Hopefully we'll do a lab where we don't ignore friction, but for this one, we're going to ignore friction. We're looking for the velocity, and we have our 3 equations: kinetic energy, potential energy, and total energy. Remember, if we ignore friction, the dissipated goes to 0. So we can use conservation of energy, which means the energy at the top of the hill is the same thing as the energy at the bottom of the hill. And energy at the top would be kinetic plus potential plus dissipated at the top equals kinetic plus potential plus dissipated at the bottom. But those dissipated energies are 0 because we are ignoring friction. If they were not ignored, if we did not ignore friction, we'd have to include it in. We could just say energy of friction. Kinetic is mv squared over 2. Potential is mgy. So we'll plug those in. And now we can plug in our numbers. At the top of the hill, the velocity is 0. So the first term, mv squared over 2, is 0. But at the top of the hill, the mass is 10 kilograms. Acceleration due to gravity is 9.8 meters per second squared, and our height above the ground is 10 meters. On the right-hand side of the equation, mass is still 10 kilograms. We don't know v squared, but we'd like to, and 2 is 2. At the bottom of the hill, the mass is still there, g is still there, but y is 0. So the whole term goes to 0. If we had started out with an initial velocity, our leading term on the left side would not be 0. If we didn't get to the bottom of the hill, but to some platform halfway up, our ending term would not be 0. So they're not always 0. It's only 0 if you start from a 0 velocity and end at the bottom. Okay, now for some math. 10 times 9.8 times 10 is 980. 10 kilograms divided by 2 would be 5 kilograms. To remove it from the right-hand side, you divide both sides. Again, if I have skipped too many steps and you need more, let me know. I'll help you fill them in. So 980 divided by 5 will give us v squared. 5 into 980 gives you 196. Square root of 196 is 14, and it's in meters per second because it's velocity. At the bottom of the hill, we're going 14 meters per second. I think this is the last example, maybe. So what's the speed at the bottom of the hill if the box has an initial velocity of 15 meters per second? So we have mass is 10 kilograms, initial velocity is 15 meters per second, y at the top is 10 meters, y at the bottom is 0. We're going to ignore friction, so we're looking for the velocity at the bottom. We know our kinetic and potential energy formulas, and we will use conservation of energy. Yay! One of my favorite things to use. So kinetic plus potential at the top equals kinetic plus potential at the bottom. Kinetic is mv squared over 2, potential is mgy. So mv squared over 2 plus mgy at the top equals mv squared over 2 plus mgy at the bottom. M is 10 kilograms. Our starting velocity is 15 meters per second. It'll have to be squared, and we divide by 2. M is 10 kilograms. G is 9.8 meters per second squared. And y at the top is 10 meters. On the right side of the equal sign, we have 10 kilograms times v squared over 2. And y is mgy at the bottom equal to 0 because y is 0. At the bottom, y is 0, so the whole term goes to 0. All right, 10 times 15 times 15 divided by 2 equals 1,125 kilogram meters squared per second squared. 10, which is a joule. 10 times 9.8 times 10 equals 980 kilogram meters squared per second squared, which is a joule. 10 divided by 2 is 5 kilograms, and times v squared because we still don't know that. Divide both sides by 5 kilograms. You end up with 420 meters squared per second squared for v squared. Take the square root of that and you get 20.5 meters per second for v. So you go a little faster if you have a starting velocity. This is why on the bobsleds, they don't just all get in the cart and let go of the brake and say, okay, gravity, do your stuff. On the bobsleds, they get a running start. All about that start. And how quick the runner, I'm not sure what they call his position on the bobsled team, but how quickly he can get his little body inside the sled. All right, let's look at roller coasters. So which roller coaster works the best? On an old-fashioned roller coaster, they drug you to the top of the first hill, which was the tallest hill. And they let you go and just gravity took over and you went whiz, whiz, whiz. And it worked as long as the first hill was the tallest, because that's your stored potential energy. When you get to the bottom, if you don't lose any to friction, boy, isn't that a perfect world, it would be turned all into kinetic, which can then push you up additional hills as you go along. If your first hill in our second example is only about half the size of your second hill, you will never get to the top. Now, do modern day roller coasters do that? No, they can control you a little better than that. So let's look at energy conservation and dissipated forces. Energy conservation and dissipated forces. So lost energy. So the energy at the top equals the energy at the bottom. So at the top, it would be kinetic plus potential. When you start a problem, you assume you haven't lost any energy yet. So at the top or at the start, there would be 0 dissipated energy. And it's only as you move that you lose some energy. If friction is where you're losing it to, then that's your dissipated energy. And remember, the energy of friction is equal to the work done by friction, which is the force of friction times the distance. So you can actually figure out the work done by friction by knowing what's your frictional force and how long is it applied, what distance is it applied over. You can get a lot out of those kinds of problems. Okay, last topic. What is power? In physics, power is work divided by time. We said work is force parallel times distance, so power could also be force parallel times distance over time. But a distance divided by a time is a velocity. It's actually an average velocity. An average velocity. I should put a little bar in there. Power is measured in watts. A watt is a joule per second. In the British unit, that's us, remember, they use horsepowers for power. Interestingly enough, I had a neighbor from Germany, and I asked him about cars. I said, tell me, in the US, we use horsepower when we're talking about a car's engine. Do they do that in Germany, or do they say watts? He said, no, horsepower. I said, okay. Be sure to do your example, your homework problem and your study guide problems on power, because there's almost always a real simple question about it. And this finishes our chapter. So we will stop and we will